Hey everybody, it's Ribley back again. We're going to talk about line integrals today. These are pretty cool, man, and they've got some pretty extensive consequences when we talk about physics. All right, we're not going to do a whole bunch of that in here, but it's going to prepare you for your physics courses in the future. I apologize for the new format. Again, fighting technical issues. I'm sure we'll get this thing squared away at some point, at which point I'm going to have to make new videos. But all right, let's get back to the topic at hand. Line integrals. Okay, here's what a line integral is. It's real simple. What we have is we've got a function floating up here in 3 space, and we've got a curve down in the plane. All right, so think of this plane down here as being like instead of a vector field, it's a scalar field, right? There are no vectors sticking out. They're just numbers. They're just multiples. They're numbers that we can use to multiply things. If you think of it in physics terms, it would be called a scalar field. All right, so what the line integral is it's the curtain that is created. If I were to take this curve C down in the xy plane and I were to shoot it up to f of xy. Now we can't see all of f of xy. It'd be kind of cooler. I guess I could with my horrible drawing, I could do, you know, here's my f of xy living up here, right? Let me change colors. Let me get a little fancy. And then here's my curve down here, right? So this is C, and then this guy up here, if you notice, I can no longer automatically set my pen. So this is f of xy up here, and this is some point, let's say, at A, and this is going to be at B, and then I draw this curtain up wherever it goes straight up. So it's moving vertically up because this is Z and this is X and this is Y. And up we go and we get that little curtain. So that would correspond here, and let's say that would correspond here, and then what I would have is that, and then I'd have that little curtain. Now, this is not so important as how we get the line integral. And down the road, we're going to talk about what the line integral is. I would bet that if I left you to your own devices, you could come up with the equation for a line integral. However, there's some notation that we have to deal with. The line integral is a single integral with this little subscript down here, c, meaning the curve. So it's the integral of that line. Well, I don't know why it's not called a curve integral, but it is what it is. Okay. Now watch. It's f of x, y. And then, what's the length of the curve? Well, we've seen this before. It's ds, right? I could write this in a Riemann sum notation. This is the limit as n goes to infinity of the sum as I goes from 1 to n of f of x sub I star, right? Because we'd have to pick some value at which we're going to shoot that up to the function. Y sub I star, and then delta s. Now, what is this ds? Oh, don't panic. We've seen that before. Remember what ds was. ds is equal to the arc length, which is going to be dx over dt squared plus dy over dt squared dt. Remember that? So this function, and I'm going to write the whole thing nice and pretty here for you, all right, is the integral across that curve. All right, it's going to have limits on it, and I'm sure with this x of t and this y of t, you're already like, oh, there's going to be some parameterization to do here, isn't there? Yes, there is. It's going to be f of xy ds, which is equal to the integral from a to b of f of x of t, x of t, y of t, and then square root of dx over dt squared plus dy over dt squared, and then out here we're going to stick a dt. Now, why is that? Let's look at this integral a little bit at a time just to make sure we understand where it comes from. This is by no means a formal proof. However, it's relatively easy to show. All right, so what are we doing? We're taking a point, right? And well, let's keep it even simpler than that. We're basically taking the length of this arc right here, and we're then doing what with it? Well, we're shooting it up f of xy. So if I take one of these little slivers right here, well, this is going to be, well, let's do it down here. This is going to be a little slice of my arc length, which we can just call this delta s, right? And then this height is just going to be, as it's right here, f of xy. Well, that's the area of a rectangle. If I add up an infinite number of infinitely thin such areas of rectangles, guess what? I got an integral. That integral is this. Now, this line integral is often called a line integral with respect to arc length, which kind of makes sense. And I'll elaborate on what it means to have a line integral with respect to something else in just a little bit, but be patient with me. Here's how cool these are. Line integrals are great for a couple of reasons. A, they're only one integral, right? It's not a single, or excuse me, it's not a double, it's not a triple integral, which we've been sort of beat to death by those, right? It's just one integral to take, which is really nice. Now, I'm going to do an example for you. I'm going to do an example. We're going to do a line integral for 2 plus x squared y ds. All right, this is just an example taken right out of the book. And I'm going to define c. C equals, let's just say, the upper half of the unit circle. All right, so we're just trying to wrap our brain around what this really means. All right, now we got to be careful here, because we gotta be careful in the way in which we define our curves. The line integrals, depend on how we trace this curve out. So if I start the curve here at A and I finish it at B, this would be C. However, if I go the other direction, like that, then this would be negative C. And predictably, just like integrating from right to left remember, if I have a function, here's my function, and if I integrate from A to B, this is f of x, and this is b, then the integral is going to be positive, right? The integral from A to B of f of x dx is going to be greater than 0, right? But if I go from right to left, then I know the integral from b to a is going to be less than 0. So line integrals can be negative because, in this case, delta x is going to be negative. In this case, delta s is going to be negative. So we do have to be careful about the way in which we define these things. Okay, so we're going to keep this one really simple. We're going to, I don't know what that did. Let's think about what's happening. This guy right here is f of xy, all right? However, there's a problem. Remember, arc lengths are always parameterized curves, true? This guy right here, well, we like to deal with parameterized curves. Now, how are we going to parameterize this? Well, it's kind of nice because if I'm dealing with the upper half of the unit circle, I know that that's the upper half of x squared plus y squared equals 1, right? And I want to just carve out, I want to start here, and I want to go like that and carve that sucker out, and then I'm going to shoot that up to this function, right? And if we absolutely had to guess, we could probably figure out what this thing is, but what it looks like, right, just by plotting points, but we don't want to do that. So let's parameterize it, and then we'll deal with it over here. Excuse me. All right, so I'm going to have an x of t, and I'm going to have a y of t. And we've done enough of this. Hopefully you see that if it's x of t, and I would prefer to start my t at 0. I can start my t wherever I want, but I want to make things as easy as possible. How about I just let that be cos t? Because if it's cos t, then when t is 0, I'm at 1, and then predictably, hopefully you can see that this guy's going to be sine t, right? Now, once I've got my x and my y here, guess what? I get to plug them in. This is what x of t is. So x of t is x in this. So this thing becomes, this is equal to, kind of all over the place with this new technology, sorry. This is going to be 2 plus cosine of t times sine squared, whoops, that should be cos squared t, shouldn't it? Times sine of t. Probably should have given myself a little bit more room. And this is going to be times the square root of what? Well, the derivatives of each squared. Well, guess what that is? Derivative of cosine is negative sine squared is sine squared t. Derivative of sine is cos squared is cos squared t. And then don't forget your dt hanging off the end, right? Well, that's 1. Now, I won't go through the whole thing with you because I'm not going to insult you. Hopefully you can take the antiderivative. This, by the way, should be like this, right? even though I'm just multiplying by 1. Excuse me. You should be able to take the antiderivative of this, right? With a simple u substitution, this is close to the derivative of cos. Antiderivative of 2 dt is 2t, and we're done. But let's talk about t for just a sec. If I'm only carving out the top half, where am I starting? Well, we already said we want to start this thing at 0 if we can. But where am I finishing? Well, I want x to be -1. So if I plug in pi, right, won't that do it? All right, from 0 to pi, yep, sine goes from 0 to 0. It passes through 1 at pi halves, and we're good. So this is the integral from 0 to pi of that. And when everything's said and done, it ends up, this is like a baking show. We end up with 2 pi plus 2/3. Okay? All right, cool. Let's crank over. Let's talk about something called a piecewise smooth curve, because this is kind of important. Piecewise smooth curve. All right, what this means is I can take a C. All right, I'm going to keep this one simple and just keep it in the xy. Now, smooth, we think of smooth as being like differentiable, don't we? Well, when we're talking about piecewise smooth, that's not necessarily the case. What we're doing is we're building a curve through smooth functions. So I can have a curve go like this. Right? I'm going to have this be C1, which is it's smooth. It looks good. It looks like I can take a derivative everywhere. We're going to start this guy. Well, I'll just start at A, right? And then I stop here, and all of a sudden I got this definitely a point of non-differentiability. But we don't really care in this case, because what we're going to do is we're just going to call it piecewise. We're building it piecewise like we would any weird function, right? And then I would call this C3. Again, I've got this nasty little chunk of non-differentiability there. But I don't, if you think about it, it doesn't really matter, because if I go back here, whether my curve is nice and pretty or it isn't pretty, when I go to find the line integral, it doesn't matter, because I can simply add each one of these individual curves together, right? Or each one of these individual line integrals together. The piecewise, we make up the entire curve. So C is equal to C1 plus C2 plus C3. So when I take the line integral, C of f of x, y, what the heck am I doing? ds, I can also say that this is the integral of C1 plus C2 plus C3 of f of x, y, ds, and then I can bust those up into individual ones. This is the line integral of C1, f of x. Well, I'm not even going to insult you guys' intelligence with that. I apologize. That's just dumb of me. This is C1 plus the integral of C2 plus the line integral of C3. All right? Which is pretty useful. That's super helpful. Now, the reason that we have to define this sort of piecewise smooth curve is because, particularly in physics, we may get particles moving in very non-polynomial ways, let's put it that way, non-pretty ways, non-differentiable ways, but they still have properties, they still do work, they still have energy, they still exert forces, and we need to be able to deal with that in physics. Okay. All right, enough said about that. So we're going to play with these a whole bunch, so don't worry about those. What I want to talk to now, hitherto what we've spoken about is line integrals with respect to arc lengths, okay? Now we're going to talk about line integrals with respect to x and y. Now, there's something crazy here that I'm gonna define it first, and then I'm going to trying to describe what really happens here, okay? But let me define it first. So what we're going to talk about now is line integrals of f along C. That's how you would say it. And this is with respect to x and y axes. And y axes, but you'll sometimes just see this written as along x and y, okay? Now, the thing that changes, so notice what changes. We're going to have a line integral, we got f of x, y, And instead of a ds, if I want to take a line integral of f along c with respect to x, this becomes dx. And what this integral turns into is the integral from a to b of f of x of t, y of t, and then x primed of t. So now we're not dealing with that entire arc length, dt. We're just dealing with it with respect to the x-axis. So think of this, if I go back here, if I'm only worried about x, then what happens here? Well, this dy over dt squared part disappears, and I end up with dx over dt, which is just x primed of t squared, the square root of that. So that's where this comes in. Similarly, I can do the same thing, but I can do it with respect to y, and this becomes the integral from a to b of f of x of t, x of t, y of t, and then predictably, right, y primed of t dt. Now sometimes, particularly in physics, you'll see it where you're dealing with issues with respect to both x and with both the x and the y axes. In other words, you're taking line integrals with respect to both x and y. And we're going to change some notation here, but this notation is going to haunt us for quite a while through vector calculus. Okay? What we're going to have is the line integral of p of xy dx plus the line integral of q of xy, because there's no law that says that these things have to be the same, these functions have to be the same functions, dy, because I can have a whole lot going on, which it can get crazy. Now, as long as we're over the same curve, the same c, I can simply say this is the integral, the line integral over, this is going to be p of xy dx, and we'll talk a little bit more about this in this section. I don't want this section to be like 9 hours long, but there are some really important topics that we're going to see in here. Whoops, that should be a y, not a dx. Sorry, I don't know what just happened there. Dy. Okay, now let me show you what this is supposed to represent, because to be honest, from a mathematical or geometric standpoint, it's really tricky to get your brain wrapped around. But from a physics standpoint, particularly when we start here in just a second, when we start talking about line integrals over a vector field instead of a scalar field, then it becomes particularly more interesting. Okay, so hold on just a sec. I'm going to grab a photo and drop it in, and I'll show you what I'm trying to what these line integrals with respect to x and y are supposed to do. All right, so this is a picture that is supposed to represent a line integral with respect to x, or the x-axis. So work with me here just a sec, because this can be a little tricky. All right, so this guy is with respect to x, because notice we got a little dx there. Remember we talked about that over here. Here is my f of xy. What we're doing is we're projecting this little slice of f of xy on to the xz axis. We're then taking from A to B on the x-axis, and that curtain that we talked about being our line integral here is just this gray curtain here. Notice, it's going to be a lot smaller in this case, isn't it? There's a lot less area, because it's like this, think of this almost like the shadow that this curtain puts on the xz plane. That's a great way to think about it. Likewise, now, with this curve, this wouldn't work for hopefully obvious reasons. Because if I try to project this thing's shadow onto this plane, I'm only going to get this little slice. And what I've got is I've got C going back and forth and forth and back between A and B. So if I simply went from here to here, that doesn't fully take into account everything that C is doing. And what we would have to do is we would have to break it up first into when it went from here to here, and then when it went from here to this other curve, and then when it went from here back to here. So this is not a great example of a curve, a parameterized curve in the xy plane, to be able to talk about line integrals with respect to y. But I did think that this is, try again, I think that they did a really nice job in showing what that line integral with respect to x looks like, okay? All right, now I know there's a lot to take in, and again, I don't want this video to be forever, but we're going to talk about two more things. We're going to talk about line integrals in space, and we're going to talk about line integrals of vector fields, because line integrals of vector fields are probably the most important aspect of line integrals because they have direct ramifications in physics. So let's talk about line integrals in space real quick. And as you can probably predict, integrals in space, the only thing that changes in space is it's still, I got this integral over c, right? And what I've got, instead of a function of x and y, again, really difficult to see what's going on in our brains, like geometrically. So instead of having a function of x and y, I've got a function of x, y, and z, and then I've got this ds, which turns into the integral from a to b of f of x of t. I keep doing that. X of t, y of t, and then z of t. In other words, it's just an extension. That's all that we're doing. And then the square root of x, I'm going to cheat a little bit here, x primed of t squared plus y primed of t squared plus z primed of t, and then squared. And then, of course, don't forget our little dt sitting there. So we should be super comfortable by now talking about this thing, or talking about these line integrals in space, even if it's difficult to wrap our brains around it geometrically. We can theoretically see how that extension just pops out to make this equation, as opposed to the other equations that we dealt with. Okay? Okay, now we're going to talk about line integrals of vector fields. Line integrals of vector fields were invented, discovered, whatever, in conjunction with physics. Now, if you recall, work is equal to the force vector dotted with the distance vector, okay? And if you recall, we've already talked about force fields as being represented by vector fields, right? We've got electric force fields, we've got gravitational fields, we've got all kinds of force fields that we've dealt with. So we've seen them before, we're not afraid. So we got this guy for free, all right? This is gonna be the force fields that we've talked about in the past, force slash, or parentheses, vector fields, okay? But we're gonna have to play around with this distance thing here just a sec. All right, what is this distance? Like, in other words, if I have a particle moving through a force field in this direction, and this is a terrible vector field, but I was just like, what the heck? And what I want to be able to do is figure out what work is done in doing so. So what I've done is I've just picked some arbitrary point P, X, Y, Z, right? And I use this little orange vector right here to denote the vector field at point X, Y, Z, okay? But now I got to worry about distance. What does that mean, distance? Well, remember the distance, when I dot this thing, this is very much like the wagon problem, right? Where I pull the wagon handle at an angle of 30 degrees, that's terrible, 30 degrees, and I've got a horizontal and a vertical component, and I dot the horizontal component with the force component, whatever this vector is that I'm pulling the handle with. If you remember from pre-calculus and even in calculus, right? We've dealt with this before in earlier chapters. When I dot these things, when I use this formula, I'm using this distance, this horizontal distance in the case of the wagon problem, but there's no quote-unquote horizontal distance. What I need is, I need a quote-unquote distance that is behaving the same way that the curve is. Well, we've seen that before. That's the unit tangent vector, right? The unit tangent vector t, I'll put a little t right there, I know that t is equal to r prime of t divided by the magnitude of r prime of t. That's the unit tangent vector, correct? But that's only 1 unit long, and that would imply that when I dot these, I'm always dotting it with something that's only 1 unit long. Well, that doesn't work, because depending on the behavior of the curve, that thing's not always going to be 1 unit long right there. So what do I do to accommodate that distance? Well, what I do is I dot f with t, and then can you think of something that would scale t out at this little sliver, this little teeny tiny chunk right here? Now, you probably guessed it. It's the arc length. It's the length, it's the change in s right there. Is that ds that we've seen before, okay? So I can describe, excuse me, I can describe the work as being approximately equal to the force at this point dotted with t times ds. Now ds is just a scalar, right? So that's what I get. Now if the work at this point is approximately this, and I want the overall, I want to add up an infinite number of teeny tiny amounts of work, well, you can probably see where this is going. This is the line integral over c in the direction of c of f dotted with t ds. Now, something really cool happens here because remember, this force field is a function of a vector field. It can literally be written as, excuse me, the integral from a to b of f of r of t, right? And then what's t? It's r primed of t over the magnitude of r primed of t. Now this is gonna, let's dial up the Wayback Machine. What is ds? What's ds? It's the arc length dt, or excuse me, it's not the arc length dt, it's the speed dt, right? All right, so that guy, if you recall, was just the absolute value. I think I said arc length when I said this. That's not, it is, but the problem is we've got a dt hanging on there. If I said that, I apologize, back it up. All right, this is the magnitude of r primed of t, which we know is the arc length, dt, right? So this right here is our t at t, capital T, and this is our ds. So look at what I get. Look really close. That tells me that work can be written as the integral from a to b of f of r of t times, well, when these cancel, look what you get, r primed of t dt. That's pretty awesome. Now, you will sometimes see this written in shorthand as the line integral of f dot dr. All right? Don't panic. I mean, you can probably see why that gets written like that. Algebraically speaking, r primed of t is dr over dt, and the dt's cancel. That's why we get this. All right? I have this guy, and I also have the line integral of f dotted with t ds, which is pretty cool. Now there's one last way that I want to describe line integrals over vector fields, and it's going to be really, really helpful for us pretty much for the rest of the chapter. We're going to see it pop up, oops, over and over again. All right, here's what it is. Given a vector field, f equals p I plus q j plus r k. Okay, so we just got a regular old vector field. We're not afraid of it. And we know that, by the way, this work is literally how we define a line integral over vector fields. So these guys are line integrals over vector fields. Vector fields. Okay, that's what they are. So you're going to be asked to find work done using line integrals over vector fields, but just think about, or line integrals, excuse me, of vector fields. Why did I write over? Of vector fields. So don't panic. They are one in the same, okay? Excuse me. All right, so given a vector field, pi plus qj plus rk, we've seen these before, we're not afraid, and the fact that these line integrals of vector fields can be written as, well, I'm going to do f dr, which is just this guy, right? This is equal to the integral from a to b of f of r of t times r primed of t dt. Now this is where we tie the whole thing up in a nice tidy little ribbon. This is the integral from a to b of pi plus qj plus rk dotted with r primed, right? Well, this is just going to be x primed of t, y primed of t, z primed of t, right? We're just talking about vector valued functions. We've been dealing with these for chapters on end, dt, of course. Well, what is p? Well, p is a function of x, y, and z. So this is the integral from a to b, of p of x of t, y of t, z of t, right? This is I. Well, should I write it like that or should I just dot it? No, let's dot it. I don't want to make you guys sit through too much of this. So when I dot these, I'm going to get dotted with x primed of t plus q of x of t, y of t, z of t, dotted with y primed of t plus r of x of t, y of t, z of t. That's r of, dotted with z primed of t dt. Now, you ready for the Wayback Machine? Let's stumble back here just a little bit. Oh, how about right here? Does that look familiar to you at all? Does that look familiar to you at all? Look at that. What I end up with is this becomes the integral of c of p dx, the line integral, over c of p dx plus q dy plus r dz. The integral of a sum is the sum of the integrals. So now we can bust it up, okay? Now, you may be going, wait, what just happened, Ripley? I don't understand. Well, no, don't freak out. What we just gave ourselves the ability to do when we take line integrals of vector fields is we can take our vector field and bust it up into its component parts. And then when I integrate with respect to x on the first guy, I integrate with respect to y on the second guy, and I integrate with respect to z on the third guy. And I get to do all my shucking and jiving and all my crazy stuff with t's, parameterization, and whatever substitutions that I want to do, but it makes for a much simple integral. Now, I could do a bunch of examples with you guys, but you'll kill me because I think we're already at like 30 some odd minutes. So this is the theory behind it. We're going to use it a ton, and we're going to spend a couple days on this. So if you're freaking out, please don't. They're really, line integrals are not difficult at all. It's just some pretty heavy-hitting theory behind it. All right, so I'll see you in class tomorrow. Have a really good day. Bye-bye.